Good day, sir. Today I will discuss all about Chapter 11 Recirculating Aquaculture Systems by James M. Ebeling and Michael B. Timmons. Oceans of the world were long considered to be an unlimited source of fishery products. Production and per capita consumption of fishery products has been continuously increasing due to the rapid increase of commercial scale aquaculture. So here are the two examples of extremely successful aquaculture products that employ intensive recirculating systems at some stage of their grow-out. These are salmon industry and tilapia. First, we have Chilean salmon industry. It has grown from 159 million US dollars industry in 1991 to exporting over 2.3 billion US dollars in 2007 or 498,000 tons. So the production of tilapia has been exponential in the last several years to the point that the US market demand for tilapia has gone from essentially nothing to importing the equivalent whole fish of 554,000 tons in 2007. So aquaculture is the most probable and feasible solution to providing the aquatic products for an ever-increasing market demand, provides a consistent and reliable source of high quality, fresh seafood that is nutritious, safe to eat, and reasonably priced. So here are the positive attributes. As a comparison, conventional aquaculture methods such as outdoor pond systems and net pen systems are not likely to be sustainable in the long term due to significant environmental issues and their inability to guarantee the safety of their products to the consumers. So indoor fish production employing recirculating aquaculture systems is sustainable, infinitely expandable, environmentally compatible, has the ability to guarantee both the safety and the quality of the fish produced throughout the year. So the indoor recirculating aquaculture system offer the advantage of raising fish in a controlled environment, permitting controlled product growth rates, and predictable harvesting schedule. So, recirculating aquaculture system conserve heat and water through water reuse after reconditioning by biological filtration using biofilters. Recirculating aquaculture system allow effective economies of scale, which results in the highest production per unit area and per unit worker of any aquaculture system. Recirculating aquaculture systems are environmentally sustainable. They use, they use 90 to 99% less water than conventional aquaculture systems, less than 1% of the land area. They also provide for environmentally safe waste management treatment. So recirculating aquaculture system allow year-round production of consistent volumes of product and complete climate control of the rearing environment. It is almost universally employed to produce salmon smolts, and designs continue to improve that are more cost competitive with conventional aquaculture systems. It also designed aquaculture systems are infinitely scalable. So the indoor aquaculture is probably the only potential method that could be used to ensure a 100% safe source of seafood, free from all chemicals and heavy metals. With increasing consumer concerns about food safety, aquaculture producers using recirculating aquaculture system have an unprecedented opportunity to meet the demands for safe seafoods. Attributes of fresher, safer, and locally raised products are clear advantages for recirculating aquaculture system produced seafood. So there are also numerous commercial systems that have opened with fanfare and have quietly gone out of business. Many of these early systems were designed using traditional wastewater treatment concepts and engineering. Next, simple trial and error approach. So the aquaculture engineering has come an age, and systems have been engineered specifically for aquaculture and the unique needs of an aquatic biological system, according to Timons and Ebeling 2010. So the species successfully being cultivated in intensive recirculating systems include tilapia, striped bass, cobia, pompano, barramundi, and marine shrimps. 11.2 Overview of System Engineering. So this is figure 11.1, unit processes used on a recirculating system. So this figure shows how a recirculation system can be divided into several individual unit processes that may correspond to separate systems or be linked together in a process stream. So the water moves from the central fish culture tank and flows through systems that remove the settlable and suspended waste solids, remove the fine and dissolved solids, convert the ammonia to nitrate, remove carbon dioxide and add oxygen, and finally, when required, disinfect the water before returning it to the culture tank. The monitoring and control system oversees all of these processes and controls the set point for water quality and sounds an alarm if they move outside of acceptable ranges. A biosecurity program and process must be absolutely superimposed on the whole process and farm to prevent losses due to disease introduction from the outside. So 10 to 20% of the discharge flow from the culture tank is removed from the center drain to take advantage of the teacup effect, which concentrates the solid in the central drain flow. Some form of settlable solids removal device like swirl separator, radial flow clarifier, and settling basin retreats this flow stream, which is then combined with the remaining 80 to 90% of the discharge from a side outlet. This combination of central drain and sidewall drain is usually referred to as a Cornell dual drain system. Remaining suspended solids are then removed usually by either a rotating microscreen filter or floating bead filter. So water then flows to some form of biofiltration such as a trickling tower, bead filter, fluidized sand filter, or moving bed bioreactor, where the ammonia is converted to nitrate by autotrophic bacteria. At high loading densities, our carbon dioxide stripping column is then required to remove excess carbon dioxide and aerate the water to saturation. So finally, where high levels of stocking density are used in commercial systems, an oxygenation device is employed to supersaturate the flow to provide sufficient oxygen. 11.3 Culture tanks. Over the years, people have used a wide variety of materials to construct tanks, including just about anything that holds water. Simple molded polyethylene tanks are often used due to their low cost, smooth surface that makes for easy cleaning, and their low weight, which allows for quick setup and relocation. They work well for the most part, but because they are very soft and malleable, they need to be well supported on the bottom. So fiberglass. Fiberglass is a popular choice for tanks because of its flexibility in both size and shape. Fiberglass tank panels are easy to cut, drill, and modify, and repairs are relatively easy. Large fiberglass tanks come in easily transported components that are field assembled to almost any diameter. For maximum strength and resistant to abuse, galvanized or epoxy-coated steel modules can be bolted together to form tanks that are extremely large and deep. The bottoms are usually poured concrete where drains and heating coils are embedded, along with the tank sidewalls. Tanks can be partially buried to conserve heat and make fish observations easier. Next, we have concrete. So concrete must always an option in making tanks and extremely strong but very permanent. Next is mixed cell raceway designs. So another option for tank design, combining the advantages of a raceway for grading and sorting and around tank for solids removal. So to promote mixing and solids removal, it is important that the tank has good hydraulic characteristics. One of the most important rules for recirculating aquaculture system is that solids need to be removed from the tank as quickly and efficiently as possible to reduce the solids' impact on water quality. Tanks can be characterized by diameter to depth ratio. This ratio should be maintained at greater than 3, less than 10, and preferably less than 5, as in a deeper tank given the same diameter. So using this range will minimize the problems of solids settling before reaching a center drain, or not settling fast enough to reach the drain by being continually resuspended. Next, we have 11.4 waste solids removal. So waste solids removal are produced in an aquaculture system as uneaten feed, feed fines, fish fecal matter, algae, sloth biofilm cell mass from biological filters. First, we have waste solids. So influence the efficiency of all other unit processes in the recirculating system. So solid removal is considered one of the most critical processes in aquaculture systems. Solids are generally classified into three categories. These are settlable, suspended, and fine or dissolved solids. In recirculating system, the first two are the primary concern, while dissolved organic solids can become a problem in systems with very little water exchange. Waste solids can be removed by either settling within the culture unit or through the use of a solids removal unit following the rearing tank. So here are the several unit process options are currently being used in aquaculture. These are settling basins, granular media filters, radial flow clarifiers, mechanical filters, and flotation or foam fractionation. Next, we have 11.5, the Cornell dual drain system. Uses the culture tank itself as a swirl separator or the teacup effect and removes most of the settlable solids from a small percentage of discharge from the center drain. This design system is applicable to round tanks and is very effective in removing the majority of large, quickly settleable solids such as uneaten feed and fecal matter using only a small portion of the total water flow in 10 to 25%. So this waste stream can then be further concentrated using either settling basins or additional swirl separators. Remember, the objective is to create a small, concentrated flow that is easily treated, rather than a large, diluted flow of waste. Solids that concentrate at the bottom center can be removed in a small flow stream by using a bottom drawing center drain, while the majority of flow is withdrawn at an elevated drain. So the dual drain system uses a center drain that removes from 10 to 25% of the flow and a higher sidewall drain for the majority of the flow. So the location of the two tank drains has typically been at the center of the tank, which then takes advantage of both the teacup effect and the strength of the overall flow when it drains through the tank center. So as we can see in this picture, this is the figure 11.2. This is a sidewall discharge box with standpipe for water level control of 75 to 90% of total discharge flow from the rearing tank. So next, so the design criteria for the percentage of flow that should be minimally be removed by the center drain are 6 liters per minute or meters per second or of tank floor area. Next, we have hydraulic retention time. Center drain is 200 minutes. And next is 15 to 25% of total tank flow rate. After calculating these three values, the largest of the three values should be used. So the final criterion that should be applied to the drain design outlet is that the tank outlet should be approximately 10% of the tank diameter. This is because if the ratio recommendation is followed, then solids should settle on the floor within about 5% of tank diameter of the tank center drain and be removed. So the alternative Cornell dual drain approach has significant economic implications. When using this approach, solids removal costs are controlled more by the volume of flow that is treated rather than the solids concentration of the effluent that is treated. By concentrating, the majority of the solid waste is only 10 to 25% of the flow, leaving a tank via the center low flow drain. Treatment costs are proportionately reduced as well. Next, we have 11.6 settling basins and tanks. A tank that provides a quiet, non-turbulent area where the flow rate is slowed and the solids are allowed to settle out of suspension by gravity. In an attempt to increase sedimentation, tube or plate settlers consisting of a sequence of inclined tubes or plates that are stacked several centimeters apart are often used. So this increases the effective settling area per unit volume and reduces the depth to which a particle must settle to contact the surface. So the advantages of settling basins are simplicity of operation, low energy requirements, and low construction costs. So the disadvantages includes relatively large size of settling basins, low removal efficiencies of small or low density particles, and leaching of nutrients from the settled solids back into the system while the solids are stored in the settling basins. So another method to increase sedimentation rate is through the use of swirl separators or hydrocyclones. The effluent water from the culture tank is injected at the outer edges of a conical tank so that the water spins around the tank's center axis. The spinning creates a centrifugal force that moves the particulates toward the wall, where they settle and can be removed continuously. These have most often been used in aquaculture recirculating systems to concentrate the solids from the dual drain culture tank system. So next we have 11.7 mechanical filters. The two types of mechanical filters are commonly used in aquaculture to remove suspended solids are screen filters and expandable granular media filters. So the suspended solids from an aquaculture viewpoint are within the fraction of total solids that will not settle out of the water column in a reasonable amount of time, 30 to 60 minutes. So this fraction of the solid waste needs to be removed from the culture tank water because of its potentially high oxygen demand and mineralization. So the increased rate of ammonia nitrogen being added to the water column as the protein and urea in the feces is broken down by bacteria into ammonia. Microscreens. So microscreens used to remove suspended solids in both research and commercial recirculating systems. They act as a form of sieve that retains suspended particles larger than the fine mesh filter screen openings. So this is figure 11.3, the rotating microscreen filter and spray bars for cleansing. So rotating microscreen filters are available in a variety of sizes and flow rate capacities. They have numerous advantages, the primary one being that they are easy to install and operate. So the screens are interchangeable and mesh size is usually selected based on characteristics of the water to be treated, required discharge water quality, and trade-offs of size, cost, and waste discharge volumes. So microscreens are especially attractive when used to remove solids from large flow streams. Additionally, they are compact in size and cause minimal head loss. So the disadvantages of these systems are high maintenance requirements and the relative high capital and operating costs. So the performance of the microscreen filter is largely dependent on size of the filter screen openings, fraction of particles removed, influencing the filter's hydraulic capacity, sludge water production rate and concentration, and lastly, filter backwash frequency that is generally discharged from the system. Next, we have 11.8, the granular media filters. Granular media filters operate by passing water laden with suspended solids through a bed of granular material, which traps the solids through sedimentation, straining, and interception. So bead filters. Bead filters is the most popular form due to their low head loss and low water requirements for backflushing. Replace the use of sand filters for all practical purposes. Next, we have sand filters. So sand filters can do a superb job at removing solids, where typically a sand bed is flooded from the top, and the water is allowed to percolate through the sand. So sand filters such as those used in swimming pools operate under the same principle, but use water pressure to force the solids laden water through the sand. When the pressure requirements to push the water through the sand become excessive, then the sand filter goes into a backwash mode and in the process discharges large quantities of water. So with either sand filter approach, excessive water loss occurs and management of either sand filter has always been a challenge. Bead filters employ small 3 to 5 millimeters low density polyethylene beads as the filtering media and pressurized upflow filters. This type of plastic media is commonly used as feedstock for plastic injection molding process. So the filtration is accomplished by trapping suspended solids particles within the bead matrix and periodically agitating the beads to settle out the trapped solids and bioflux. So these filters have been successfully used for both solids capture and biofiltration. Traditionally, the chief disadvantage of this type of filter has been the large volume of water required for backflushing, although much less is required than in a sand filter design. Although the polygazer class of bead filters have successfully addressed this problem. Many of the fine suspended solids and the dissolved organic compounds that build up over time in intensive recirculating systems are not removed by mechanical filtration or granular media filters. These solids can be removed by using a process usually referred to as foam fractionation, air stripping, or protein skimming. In this process, air bubbles rising, air bubbles. Sorry for that. So in this process, air bubbles rising through a closed contact column physically absorb the fine suspended solids and dissolved organic compounds onto the surfaces of the air bubbles. The bubbles create foam at the top of the liquid column and the organic waste can then be disposed of along within the foam produced. Next, we have 11.9, the disposal of the solids. Solids generated by these removal methods can have significant impact on the environment if not disposed of appropriately. In general, aquaculture solid waste are treated as an agriculture waste and considered a non-toxic nutrient source. Several options are utilized for disposal, including agricultural application on land and composting. Land application of waste solids to an on-site agricultural field is usually the cheapest methods of solids disposal. Land application is governed by regulations that limit the amount of pathogens, heavy metals, and other contaminants like nutrient content, soil type, and plant nutrient uptake characteristics to prevent runoff or groundwater contamination. One of the newest techniques for containing sludge is to use geotextile bags. The geotextile bags are porous textile bags that receive the waste stream and capture solids while allowing the water to drain off for recapture. Polymer or flocculation agent. This is the added to the influent to improve solids and liquid separation. Next, we have allium or ferric chloride. Can also be added as a coagulation aid, which also helps to sequester dissolved phosphorus. Composting of waste solids using thermophilic bacteria creates a valuable soil amendment and also can be used to dispose of fish mortalities in a safe manner. Anaerobic and aerobic waste lagoons can be used, but will require careful engineering design to be properly sized and managed. Next, we have 11.10, the biofiltration. This figure, 11.4, this is the geotextile bag on gravel bed designed to capture leached water for reuse. Nitrogen is an essential nutrient for all living organisms and is found in proteins, nucleic acids, adenosine phosphates, pyridine nucleotides, and pigments. So in the aquaculture environment, there are four primary sources of nitrogenous waste. These are urea, uric acid, and amino acid excreted by the fish, organic debris from dead and dying organisms, uneaten feed and feces, and lastly, nitrogen gas from the atmosphere. So various nitrogenous waste products are expelled by fish through gill diffusion, gill cation exchange, urine, and feces. The decomposition of these nitrogenous compounds is particularly important in intensive recirculating aquaculture systems because of the toxicity of ammonia, nitrate, and to some limited extent, nitrate. Nitrification. So this is the process of bacterial-driven ammonia removal in a biological filter and consists of the successive oxidation of ammonia to nitrate and finally to nitrate. Denitrification. The reverse process and is an anaerobic process where nitrate is converted to nitrogen gas. The nitrification process is becoming increasingly important. Hoy nga naman! Especially in marine systems, as stocking densities increase and water exchange rates are reduced, resulting in excessive levels of nitrate in the culture system. So nitrification is a two-step process, where ammonia is first oxidized to nitrate and then nitrate is oxidized to nitrate. The two steps in the reactions are normally carried out sequentially. Since the first step has a higher kinetic reaction rate than the second step, the overall kinetics are usually controlled by ammonia oxidation, and as a result, there is usually no appreciable amount of nitrate accumulation. So, these are the equations 1, 2, and 3. This shows the basic chemical conversions occurring during oxidation by nitrosomonas and nitrobacter and the overall oxidation reaction according to US EPA 1975. Based on these relationships, 4.57 grams of oxygen and approximately 7.14 grams of alkalinity are needed for the complete oxidation of 1 grams of ammonia nitrogen. Alkalinity. All alkalinity is measured or defined in terms of calcium carbonate is generally added by using sodium bicarbonate or baking soda, or calcium carbonate, slaked lime, or hydrated lime. Sodium carbonate has the advantage of being rapidly dissolved and being very safe to handle. Conversely, the various lime compounds are not easy to dissolve, and they are dangerous to handle. The lime products, though, are often much less expensive per unit of alkalinity than baking soda. Ammonia removal capacity of biological filters is largely dependent upon the total surface area available for biological growth of the nitrifying bacteria. For maximum efficiency, the media used balance a high specific surface area with appreciable voids ratio for adequate hydraulic performance of the systems. So media used in biofilters must be first inert, second non-compressible, and non-biologically degradable. So the typical media used in aquaculture biofilters are sand or some form of plastic or ceramic material shaped as small beads or large spheres, or rings or saddles. So biofilters must be carefully designed to avoid oxygen limitation or excessive loading of solids, and biochemical oxygen demand or ammonia. So here are the several types of biofilters commonly used in commercial intensive recirculating aquaculture systems. These are trickling biofilters, floating bed filters, fluidized bed biofilters, downflow microbead filters, and moving bed bioreactors. Next, we have 11.10.1, the trickling towers. Trickling tower is a classical biofilter combining both biofiltration, aeration, and degassing into one unit process. Water cascades over some media on which bacteria grow, oxygen diffuses into the water, and nitrogen and carbon dioxide diffuse out. They can be constructed to any diameter required. Effective distribution of the influent water over all the media, both horizontally and vertically, is a continual challenge. Next, we have 11.10.2, the floating bead filters. So in this figure, 11.5, this is the propeller washed bead filter for biofiltration and solids capture. Floating bead filters use beads that are slightly buoyant. The beads provide surface area for bacteria and also trap solids, thus doing two jobs for the price of one filter. Water is introduced below a bed of packed bead media and travels upward through the filtration chamber, where mechanical and biological filtration takes place. Backwashing of the filter is accomplished either mechanically with a motor propeller or with air bubbles rate. A desired backwash or mixing cycle will be imposed to clean the beads and remove the resulting sludge. So newer designs for bead filters have the capacity to minimize water loss during the cleaning cycle. This is particularly advantageous in marine systems where the loss of salt water is minimized and thus operating costs are decreased. Next, we have 11.10.3 fluidized sand beds. So usually is used in large-scale cool or cold water applications and provide large surface area for bacteria in a small footprint. These filters get their name because as the water flows up through the sand bed, the sand becomes suspended in the flow or fluidized. Numerous designs have been investigated and found to perform effectively, particularly for cool water applications that use fine sands. Fluidized sand beds can be relatively more expensive to operate than other filters due to the high pump rates and pressures required to fluidize the sand bed. Next, we have 11.10.4 downflow microbead biofilter. This is used for several years due to their simplicity and low cost for media. The filters use small plastic beads 1 to 3 millimeters that float in the biofilter as the water flows down through them. The high specific surface area, low head loss, and small footprint makes them a strong competitor to other biofilters designs. The styrofoam microbeads are also a fraction of the cost of other media. Next, we have 11.10.5, the moving bead bioreactors. These have been introduced over the last several years and appear to be one of the most competitive of all the biofilter types. The media remain in suspension as the water flows through the biofilter, which is actively aerated. The high turbulence and aeration provide good mixing and contrast with the media. Next, we have 11.11 choice of biofilter. In this figure 11.6, this is the media and discharge manifold and in MBBR. One of the chief advantages of both the trickling biofilter and the MBBR is that they both add oxygen to the water flow during normal operation. They can provide some carbon dioxide stripping. In contrast, the submerged biofilters, floating bead filters, microbead filters, and fluidized bed biofilters are all net oxygen consumers and must rely solely on the oxygen in the influent flow to maintain aerobic conditions for the biofilm. If, for whatever reason, the influent flow is low in dissolved oxygen or the incoming flow to the biofilter is too low, interrupted anaerobic conditions will be generated within the biofilter. The application of low specific surface area media is a distinct disadvantage for both the trickling biofilters and the MBBR. Since the capital cost is proportional to the total surface area of the filters, the result is physically large and requires more costly filters. In contrast, floating bead filters and especially fluidized bed filters and downflow microbead filters use media with the high specific surface area, resulting in reduced cost and space requirements for the equivalent surface area. Next, we have 11.12 aeration and oxygenation. So this figure is the space cone for oxygen transfer. Dissolved oxygen is the first limiting factor in intensive aquaculture systems. Minimum dissolved oxygen concentrations of from 4 to 6 milligrams per liters are required for optimal growth and survival of most aquaculture species. At densities up to 45 kilograms per meter cube aeration with atmospheric oxygen is adequate to maintain this level and is commonly referred to as aeration. At higher stocking densities, pure oxygen is required and is usually referred to as oxygenation. So during aeration, air is brought into contact with water, either by bubbling air through the water or forcing small droplets of water through air. In each case, oxygen is transferred into the water and to some extent carbon dioxide and nitrogen are stripped out. Oxygenation process. So, pure oxygen is used to increase the transfer rate and yield supersaturated oxygen concentrations, theoretically 5 times that of aeration with atmospheric oxygen. Oxygen can be produced on site using pressure swing absorption, equipment of purchased in bulk liquid or gas form from commercial sources. So these are the numerous types of oxygen transfer equipment that are now available from commercial sources. This includes U-tubes, packed columns, packed columns, multi-stage low-head oxygenation units, pressurized columns, oxygenation cones, oxygen aspirators, bubble diffusers, enclosed mechanical surface mixers. The two most often used in large-scale commercial systems are the downflow bubble contractor and multi-stage low-head oxygenation unit. So the downflow bubble contractor, it consists of a cone-shaped column with water and oxygen injected at the top and removed at the bottom. As the water and the oxygen bubbles move down the cone, the downward velocity of the water decreases due to the increasing cross-sectional area until it equals the upward velocity of the oxygen bubbles. This yields a long contact time between the oxygen bubbles and the water, resulting in the oxygen diffusion efficiencies at or above 90%. So next, the multi-stage low-head oxygenation unit. So it increases oxygen transfer efficiency by reusing the oxygen feed gas through a series of contact chambers. Water flow is distributed equally through a series of chambers via a perforated plate, flows through the chambers and into a pool of water, which seals the lower outlets. Oxygen gas enters at one side of the series of chambers and passes through each chamber due to the pressure variation across the unit. The repeated contact of oxygen and water in each chamber provides a high rate of gas transfer, both oxygen into the water and excess nitrogen out. So LHOs provide moderate oxygen transfer efficiency and operate at very low pressure heads. Gas to liquid ratios should be maintained at less than 1.5% to obtain reasonable transfer efficiencies. Next, we have 11.13 carbon dioxide removal. Carbon dioxide is a product of respiration of fish and other organisms in the production system, such as the bacteria and the biofilm. At low stocking densities, carbon dioxide is removed by the physical agitation and exposure of the water to air. But advances in a recirculation system, design, and management have resulted in a steadily increasing stocking density of fish and a reduction in water exchange rates. As a result, carbon dioxide often becomes a limiting factor in some intensive production systems. So for every gram of oxygen consumed, 1.38 grams of carbon dioxide is produced. Carbon dioxide obstructs the respiration of fish by reducing the capacity of the blood to transport oxygen through a physiological phenomenon known as the Bohr effect. Carbon dioxide also directly affects the overall system performance by decreasing its pH, so which can stress the fish and inhibit the nitrifying bacteria in the biofilters. So carbon dioxide can be controlled by gas exchange and a downflow trickling tower or packed column aerator similar to the downflow trickling tower used for biofiltration. As the water containing carbon dioxide flows over the media in the column, air is forced either up or down the column and carbon dioxide is removed by gas transfer across the thin water or air interface on the media surface. So carbon dioxide removed by gas exchange is often limited by the buildup of carbon dioxide in the gas phase, requiring gas to liquid flow ratios substantially higher than those needed for traditional oxygen or nitrogen gas transfers. So the gas liquid ratios should be maintained above 5 for effective removal conditions. So carbon dioxide concentration in culture waters will also be impacted by the alkalinity concentration of the water. In fact, there is a stoichiometric relationship between pH, carbon dioxide concentration, and alkalinity concentration. Any two of these three variables defines the third variable. Next, we have 11.14 monitoring and control. As the stocking density of fish continues to increase, the need for continuous monitoring and control of critical operations such as water flow, tank water level, and oxygen concentration also becomes essential to prevent catastrophic fish losses. Takes only one mistake to kill everything in your facility. Today, continuous monitoring systems are commercially available and relatively reliable. All the alarms should report to a phone dialer to notify staff both during and after working hours. Monitoring and control systems can be as simply as a solenoid valve that automatically opens an oxygen supply line to aerate during a power failure. For most facilities, simple, fairly inexpensive monitoring auto-dialer systems are commercially available, which will monitor 8 or more switch inputs and automatically switch on backup systems and dial out in emergency situations. At the other extremes are sophisticated computer control systems that monitor multiple parameters with redundant backup systems, internet pages for offsite monitoring, and phone dialers to alert management of system status and alarms. Regular monitoring of other parameters that change slowly with time requires a well-equipped and maintained water quality lab. It doesn't have to be an elaborate, expensive facility, but it needs to be in a dedicated location with all the support equipment for good laboratory practices. Next, we have 11.15 Current System Engineering Design. Designing recirculation system seems more like ordering from a Chinese menu, where the designer selects one unit from column A and another from column B and another from column C and then integrates them into the optimal design. These are the important design questions that determine what unit processes to use includes species to be produced, stocking density, production capacity, and sensitivity of species to water quality parameters such as temperature, dissolved oxygen, ammonia nitrogen, pH, and carbon dioxide. So for example, tilapia is a species with excellent market potential and tolerance to poor water quality. Many marine species of commercial interest have very high water quality requirements. Numerous combinations and permutations of the above unit processes have been implemented over the past decade, and although no one system design has become the standard, several combinations seem to work well together. Although microscreen filters have a high capital cost, their ease of installation and operation make them economically attractive. Most biofiltration is now accomplished with either a moving bed bioreactor or some form of granular media filters, such as a downflow bead filter or a fluidized sand filter. The main advantage of the moving bead bioreactor are aeration and degassing they provide, reducing aeration or oxygenation requirements. Fluidized sand filters have the advantage of lower cost, lower capital cost and smaller size, but higher operating cost. Aeration and degassing of carbon dioxide is usually accomplished with some form of cascade column with high air, water volumetric ratios. Finally, oxygenation of the recirculated water is usually performed with the downflow bowel contractors or LHOs. Next, we have 11.16 Recirculation System Design. 11.16.1 The mass balances loading rates and fish growth. All systems designs should begin with a mathematical analysis of the system loadings. Water flow is the mechanism by which oxygen is transported into a fish culture vessel and the waste products being generated within are removed. So the design of a recirculating aquaculture system should ensure that the important parameters affecting water quality and fish productivity are properly balanced. This requires calculating the required flow rates via mass balance equations to maintain the design water quality variables at or below their maximum tolerable or design target values. System must operated at the highest flow rate calculated for these four critical water quality parameters. Obviously, the maximum flow rate used to maintain the constraining water quality parameter will be higher than necessary for the others, which simply means these water quality parameters will be at better values than design targets. The same mass balance approach can be utilized on any variable affecting water quality. The mass balance approach simply comes down to balancing the transport in some parameter, the production of this particular parameter within the culture tank, and the transport out of the parameter. So in word equation form, this is the word equation form. Transport in of X plus production of X is equal to transport out of X. So the production term can be the production of oxygen, ammonia, suspended solids, or the CO2. Note that the production term can be negative, meaning consumption of a certain component. Note that X does not refer to a concentration of X, for example, in milligrams per liters, but rather about a mass quantity of some stuff referred to as X in the word equation. This is the control volume approach. Engineers like to depict mass transport across some imaginary box that designates the vessels or container that we're trying to analyze. For RAS, it can be assumed that the culture tank represents a completely well-mixed tank and that the tank has reached a non-changing condition with respect to time or steady rate conditions. Each of the boxes shown in figure 11.1 represents some treatment device or process that changes the concentration of the noted parameter X. Note, there could be several treatment devices, each treating a different water quality variable. Another way of representing the mass balance equation uses the product of the flow rate, volume over unit time, multiplied by the concentration of mass per volume, resulting in a mass per unit time, as of for example kilograms of oxygen per day, kilograms of solids per day, and etc. So this is the mass balance equation. So this is the mass balance equation in its simplest form. 11.16.2 Selecting tank values. Designer manager must choose design or target operating conditions to calculate the mass balances. These are the C values in the mass balance equation. These design numbers are species dependent and are continually being refined for RAS applications. Calculating the minimum flows required to maintain targeted values for water quality will show how desensitive the calculated flow rates are to the values selected for the design value. A typical scenario is to select a value, do the calculations, realize that there is no way you could afford to supply such as a high flow rate, and then start to make adjustments in the targeted value. In the end, one must choose realistic values at the beginning of the design process and then stay with these choices and the ramifications of the resulting flows required to maintain the mass balances. Do not ever compromise on the required flow rates. Next, we have 11.16.3, the water treatment device. Each treatment box is a system that improves the water quality of the water. The concentration of the particular water quality parameter leaving the treatment device can be calculated by knowing the absolute best the treatment device could achieve and the treatment efficiency of the particular device being used. The treatment efficiency should be provided by the device supplier and manufacturer. Solving the general mass balance equation applied to the treatment box determines the concentration of each particular water quality parameter leaving the treatment device. The treatment device could be a biofilter, a CO2 stripper, or a solid settling chamber. Each will have its own treatment efficiency for the particular water quality parameter it is designed to treat. So, the water quality concentration, C, out leaving the treatment box is found by using a mass balance analysis to B. So this is the equation. So in this equation, T is the treatment efficiency or percent and C best is the absolute best result obtainable by a treatment system. Note that if the device is an oxygen addition unit, the C best term can be increased above atmospheric concentration values for oxygen by increasing the partial pressure above the atmospheric oxygen partial pressure in the device. For example, a pure oxygen device will have a C best value of roughly 5 times the C best value obtained if normal air were used at atmospheric pressure. C best for most other parameters should be fairly obvious to the reader. So 11.17 for major water treatment variables. First, we have 11.17.1, the oxygen. So the major reason most fish die is from lack of oxygen due to a loss of water flow. This is because oxygen is consumed at a fairly high rate or fish metabolism, and oxygen is transported by water flow. Due to low inherent concentrations of oxygen, high flows are required to transport the required oxygen. Flows required to maintain a satisfactory oxygen level are generally the controlling flow rate parameter when solving the series of mass balance equations to determine the most restrictive parameter. Even a partial loss of flow will generally result in insufficient oxygen for the fish, resulting in death. Ask yourself if your monitoring systems will sense a reduction in flow as opposed to a loss of flow. It is important to remember that not only do the fish require oxygen, but also the biological filter, which is critically dependent upon adequate oxygen levels to support bacteria metabolism. The dissolved oxygen concentration within the filter must be maintained at or above 2.0 mg per liter to ensure that the rate of nitrification in the filter does not become limited because of oxygen depletion. Always measure the DO coming out of the biofilters, and if the concentration starts to approach 2.0 milligrams per liter, then take corrective action. So the production term for oxygen is, so this is it. The production term of oxygen is equals to negative 0.25 kilograms per kilogram feed consumed by fish, 0.2 kilograms per kilogram feed consumed by nitrifying bacteria, and negative 0.13 kilograms per kilogram feed consumed by heterotrophic bacteria, can be as high as 0.5 and is equals to 0.50 kilograms or the sum of above per kilograms for feed for system. These oxygen terms are all negative since they consume oxygen from the system as opposed to be adding a mass quantity to the water column. The heterotrophic bacteria load can be as much as 0.5 kilograms of oxygen per kilograms of feed fed or higher if the system has poor solids removal. The oxygen consumption term is always much higher when solids management in a recirculating aquaculture system is not good. A safe number for design purposes might be closer to 1 kilograms of oxygen per 1 kilograms of feed used. This would be twice as high as the above suggestion. 11.12.17.2 The ammonia. So there is considerable confusion about design target values for ammonia concentration. Definitive values for the toxic levels of ammonia and the differentiation between the toxic NH3 form and the supposed non-toxic NH4 positive have not been precisely determined. The apparent toxicity of ammonia is extremely variable and depends on more than the mean or maximum concentration of ammonia. For a more precise estimate and one that is affected by protein content, the following equation for the production rate of ammonia can be used. F is the daily feeding level and PC is the protein content of the feed being fed. In this equation, the time period used is 1 day. In recirculating aquaculture system, feed can be fed uniformly over a 24-hour period, thus distributing the ammonia load uniformly over the entire day as well. If a uniform 24-hour feeding is not used, then the above equation should be adjusted and the time period should be the time between feedings. Or if a single feeding per day is used, then use 4 hours as a time period as an estimate of the time for the ammonia to be excreted from a feeding event. Note that in the above equation, the feed is assumed to be fed uniformly over a 24-hour period. If the feeding period is concentrated to some fraction of the day, then the production equation for tan must be accordingly adjusted upward. For example, if you feed over a 12-hour period, then the P-tan term will be twice as large for design purposes, requiring your biofilters to be twice as large. This is why in recirculating aquaculture system, you generally feed the fish over a 24-hour period when possible. Next, we have 11.17.3, the carbon dioxide. So it is an important but largely overlooked water quality limiting parameter. This is probably because until recently, most systems were generally low density. This type of management also kept CO2 values at low levels. However, loading rates have increased in recent years and it has become necessary to inject pure oxygen into these systems instead of using aeration. As a result, the natural stripping of carbon dioxide that occurs when using aeration systems was no longer taking place. Carbon dioxide production can be explicitly related to oxygen consumption as the ratio of molecular weights 44 by 32. 11.17.4 The suspended solids. The effective control of solids generated in RAS is probably the most important task that must be accomplished to ensure long-term successful operation of our RAS. The quantity of suspended solids or total suspended solids generated per unit of feed being fed is estimated as this is the estimation. So TSS is treated as a dilute waste. TSS design concentrations in RAS will be in the 10 to 100 milligrams per liter range, even after concentrating TSS with some type of treatment process, such as a rotating screen filter. The discharged water will still contain only around 0.5 to 1% solids on a dry matter basis. In comparison, cow manure is 20% solids. TSS captured in a settling basin has a fluffy consistency and will require substantial volumetric space depending upon frequency of cleaning. As a rule of thumb, assume that each kilogram of dry feed fed will produce approximately 25 liters of liquid waste or 1% solids. Next, we have 11.17.5, the nitrate nitrogen. Nitrate nitrogen is not considered in the mass balance equations to determine maximum required flow rate. In saltwater system, though nitrate should be considered, nitrate nitrogen is the end product of the nitrification process. In general, concentrations of nitrate are not extremely adverse to RAS water quality. Nitrogen is essentially conserved throughout the nitrification process. Thus, if 1 kilogram per day of TAN is being produced, then 1 kilogram of nitrate is being produced. The equilibrium concentration of nitrate will therefore be directly dependent upon the overall water exchange rate throughout the system. So nitrate nitrogen is relatively non-toxic to freshwater fish and as such will not influence the controlling flow rates in the system. One can choose some values such as 200 milligrams per liter if you want a number to work with. More recent unpublished information seems to indicate that for various salmonids, the nitrous levels should not exceed 40 to 50 milligrams per liter. So the design information is very limited relative to this water quality parameter, especially for saltwater system. Next, we have 11.18. This is the summary of 4 production terms. These 4 terms are called the production terms or the P terms in mass balance equation. Summarizing the 4 production terms are related to feed being fed is as follows. So we have the P oxygen is equals to negative 0.50 kilograms per kilogram of fed consumed by fish. The P carbon dioxide is equals to 1.375 grams produced for each gram of oxygen consumed. P10, we have F times PC times 0.092. And the P solids is equals to 0.25 times the kilogram feed fed, the dry matter basis range of 0.20 to 0.40. 11.18.1 Predicting fish growth. So the basic premise of RAS engineering is to produce a given volume of market-sized fish at some predetermined schedule. Based on the growth rate and stocking density, the size and number of production tanks can then be estimated. The production rate also defines the required fish feeding rate, which then in turn determines the waste regeneration loads and also oxygen consumption rate. Based on this data, the most appropriate treatment systems can then be designed to based on the both water quality demands and economics. So this is the table 11.1. This is the temperature growth units in degrees per Celsius and degrees of Fahrenheit for trout, tilapia, yellow perch, and hybrid striped bass. So a common way of defining fish growth is based on existing data sets of production trials under commercial stocking densities, feed rates, and water quality conditions. A second way is based upon a temperature unit approach, and some defines number of temperature units to create a unit growth rates, such as centimeters per month. So this is in this figure, this is the above equation predicts growth using units of centimeters per month or inches per month. And the T values are all in either degrees centigrade or Fahrenheit. The growth equation is subject to the limitations that if T is greater than T max, then calculate the growth at T max. Note that excessive temperatures will compromise growth and or feed conversion. Next, we have 11.19, the stocking density. The final and most important question that must be addressed in system design is the mass of fish that can be maintained in a tank, or more appropriately, the mass of fish that can be maximally supported. We should probably call this term the harvest density. The number of fish and their individual weight will define the feeding rates from which all other individual engineering components are designed. The mass of fish that can be stocked per unit volume will depend on both the fish species and the fish size. We use an approach that is based upon body length to estimate the number of fish that can be carried per unit volume tank. So this is the estimated number of fish that can be carried per unit volume tank. So the maximum allowable of safe densities for fish stocking is primarily a function of fish size, species, and the characteristics of rearing environment and management skills. New growers tend to overestimate their own safe loading densities and assume that they can establish and sustain densities from the very beginning that in fact require expert management skills. Do not fall into this trap. You will kill fish. New growers should target about half the densities recommended for expert growers. For example, a tilapia system for a new grower should probably be operated at a maximum density of 50 kilograms per meter cube, rather than 100 to 120 kilograms per meter cube. So 11.20 we have engineering design examples. So 11.20.1, this is the required minimum flow rates. In this table, we can see the condition factors for various fishes by Timons and Ebeling 2010. So let's assume a target production capacity of 500 metric tons of tilapia per year with a target market size fish of 750 grams, whole on ice. Tilapia fingerlings are purchased at a mean size of 50 grams. A three-stage production system is decided upon. So the step 1 is to calculate growth period from stocking to harvest. Next, the step 2 is to determine time for grow out. So in step 3, this is the determine production strategy. So in step 4, we have the calculate weekly harvest weight. Step 5, we have determining the number of each tank at harvest. And that's step 6, estimate final tank biomass at each stage. And step 7 is the estimate final feed rate per tank. So in this table 11.3, we can see this is the initial and final weights and weights of the three-stage production strategy. So step 8, we have the determine the controlling flow rate for these design problems. So this is the table 11.14, the K calculations parameters used for the grow out stage. And 11.20.2, required design flow rate for dissolved oxygen. Note that using 0.37 kilograms oxygen per kilograms of feed would be the lowest demand one would use for design purposes. This would represent the case where either a trickling tower or MBBR is to be used. As previously discussed, using a value of 0.5 to 1.0 for oxygen demand would be a more conservative approach to ensure sufficient flow for all oxygen demands in the system. 11.20.3, the calculating tank sizes. The last step in our design process is to determine the tank sizes necessary for each of the three stages for our 500-ton production farm. The tank size can be determined based on the allowable fish biomass stocking densities. As previously determined, the final fish biomass per tank was 2,195 kilograms for the fingerling stage of stage 1 and 5,134 kilograms for stage 2 and 10,000 kilograms for the grow out tank stage 3. Note how the system supports larger biomasses of fish as the fish increase in size. This is because the fish requires space or room by length and not by body mass, and mass is proportionally to length cube. Correspondingly, the stage 2 final tank density is 110 kilograms per meter cube, and the grow out tank stage 3 at harvest is 137 kilograms per meter cube. The required volume of each tank for each of the three stages is equal to the total biomass for that stage cohort of fish divided by the stocking density, or for example, this one. So now we have 11.21, the conclusion. The design and engineering of intensive recirculating aquaculture systems has made significant progress over the past several decades. Systems components have been designed and engineered especially for aquaculture and are field tested and available from several commercial sources. System integration is just beginning to be investigated to determine optimal configurations of an overall system design based on species, production levels, and water quality requirements. Even with all the successes and improvements, though it is still challenging to implement and manage recirculation systems that are most competitive with other less capital intensive production strategies. This end of the slide. Thank you for listening.